Okay, hello everyone. My name is Jiaju Chen from University of Science and Technology of China, and it's my pleasure to present our work at SIGIR today. And the title of our work is Treatment Effect Estimation for User Interest Exploration on Recommender Systems. And let me illustrate the motivation of our work first. Okay. Recommender systems learn personalized user preference from user feedbacks, like clicks, and give recommendations to maximize user satisfaction, like CTR. And the problem is, current recommender systems are biased to partial user interests. Due to the exposure bias, the recommender systems can only observe part of the user's interest, and the user's hidden interests are unexplored. So, to solve the bias problem and maximize overall CTR, we must explore the hidden interests of users. And existing works on user interest exploration falls into three groups: debiasing methods, diversity-oriented methods, and bandit algorithms. For debiasing methods, they use different techniques to alleviate the bias, but they fail to actively discover new interests. And for diversity-oriented methods, they do not consider the reward-cost ratio, and they may recommend irrelevant items that harms accuracy. And for bandit algorithms, they consider the trade-off between exploration and exploitation, but the cost of their exploration is high, and they lack global scheduling. So back to our work. Let's first pay attention to the insights of exposure ratios of each categories. Suppose users have specific exposure ratios preference for each category of items. No, too much exposure may cause burden, since the user may go bored to see all the same categories, while too little leads to unknown preference. And the key is that we need to estimate the CTR given different exposure ratios, and that is the treatment effects. So in general, we divide our work into two steps. In step one, we estimate the treatment effects. Specifically, we regard the treatment as the category exposure ratios and the outcome as the CTR given specific treatment. And in step two, we maximize the outcome using the treatment effect estimated. We attribute it to a constraint optimization problem where we maximize overall CTR and given the constrained treatment. Okay. The treatment estimation task is similar to the concept of uplift modeling, and which aims to estimate the effect of the treatment. However, there are several challenges. Number one, in recommender systems, we lack randomized controlled experiments, which are hard to obtain since they harm the user's satisfaction. And number two, there are intrinsic bias. That is, as we can see in figure B, the behavior history X affects both the treatment T and the outcome Y, which leaves a backdoor path from T to Y through X. And number three, our estimation is multivariate and continuous, which needs extensive data. And so now let me illustrate the methodology of our work and show how we handle the challenges. And to begin with, let me introduce some basic concepts of the treatment effect estimation. First, the treatment TU, which is a vector of the treatment of different categories for user U. Here, it means the exposure ratios of different categories. Second, the outcome YUT, which is a vector of the outcome of different categories given specific treatment T for user U. Here, it means the CTR of different categories given exposure ratios T. Third, ADRF, abbreviation for average dose response function, means the expectation of the outcome given treatment T. And fourth, MTEF, abbreviation for marginal treatment effect function, means the marginal effect of the ADRF at treatment T. And there are also some assumptions which uplift modeling usually use. Number one, steady unit treatment value assumption assumes that all users are independent and will not affect each other. And number two, unconfoundedness assumption assumes that treatment and outcome are independent given the observed variable X. In our work, we regard users' behavior history as the confounder. And number 3, overlap. Assume that there is a probability for every treatment. And due to the lack of the randomized controlled experiments, we consider the heterogeneous effects of estimation. Effect estimation considered among the user groups. That is, we use ADRF estimated from a group to represent the ADRF of a single user. And after estimating the ADRF, we are solving an optimization problem and to maximize overall CTR using the constrained exposure resources. Okay. So since we want to estimate the effect of each category, the number of categories cannot be too large. So we first cluster the categories, use k-means. And then we generate the augmented data sets to gain the treatment and outcome information of each user sample. Given user's interaction trail, we take the former lambda interactions for behavior histories and the latter 1 minus lambda interactions for treatment and outcome computation. And due to the confounding bias, we must calculate the propensity of treatment T given behavior history X first. Since we found that the propensity is hard for networks to predict, and we choose to calculate the propensity in a statistical way, and like the equation here. And it's worth noting that we utilize a discretization function that maps continuous values into integers. And by doing so, we turn the continuous treatment into discrete ones, which greatly reduced the challenge of data sparsity. And after the discretization and computing the propensity, we can now estimate the ADRF in a C times K plus 1 matrix form, where C is the clustered category number and K is the discretization number. And using the following equation, we can estimate ADRF using an IPW way, where gamma is the propensity exponent controlling the extent of the IPW module. And after computing discretized ADRF, we find that the constrained optimization problem turns into a knapsack problem, and we can use dynamic programming to solve it in linear time. As we can see in the figure A, you can see the optimum of treatment marked by the red star without the AT1 constraint. The AT1 constraint is that all the treatment, the sum of the treatment vector must be 1. And after we add the constraint, the distribution shifts and to achieve the optimal overall CTR. However, since data sparsity greatly affects ADRF estimation, we can consider a simplified version, MTEF estimation. We calculate the uplift effects around a fixed treatment T0. When treatment is discrete and delta T is 1, MTEF is the difference between two consecutive ADRF. And when we use MTEF for rec, we first obtain the default treatment T0 and then estimate the MTEF and re-rank the scores using the following equation. And in the end, let's review the challenges and how we solve them. Number 1, we generate datasets to substitute the randomized controlled experiments. And number 2, we use IPW to debias the confounder bias. Number 3, we discretize the multivariate continuous treatment and cluster categories to make the best of the data. Okay, so let me now show you the experiments. Okay, we choose 3 real-world data sets, Yahoo R3, Code, and Quirec as our data sets. These data sets contain the randomized controlled data, and we choose them as the unbiased data to test the model's capacity to explore users' hidden interests. And for baseline, we choose MF, FM, and LightGCN as the backend models, and IPS, BC loss, and IDCF as debiased models, AMR and PM alpha beta as the diversity-oriented methods, Lean UCB and HCB as bandit methods. And for metrics, we choose common accuracy metrics like recall and NDCG, and we also choose recall recalls of the unexpected items and recall of the unpopular items to test the ability to mine the user's hidden interests. And here are the results. For each dataset, we choose a model with the highest recall in MF, FM, and LIGCN as a backend model. And given the overall performance above, we can find that uplift RAC MTEF significantly outperforms all other baselines on both accuracy and serendipity. And we also tried different backend models for uplift RAC MTEF and found that uplift RAC MTEF significantly improves all backend models' performance, which testify that our method is model agnostic. And to testify the impact of IPW module, we choose different propensity exponent gamma, from 0 to a very large number, and to test and record its performance. We found a proper non-zero gamma optimized uplift RAC MTEF's performance, which means that the IPW module works. And we also do experiments to see the performance difference between uplift RAC MTEF from uplift RAC ADRF. In Yahoo's R3 and the code, uplift RAC MTEF and ADRF both outperforms the backend models. And in QuiRac, a short video dataset, uplift RAC ADRF fails to perform well. We attribute this unstable performance to the variance generated during the ADRF estimation. Okay. And we also do hyperparameter analysis on the category clustering number C and the dividing ratio lambda. We found that clustering items into relative small groups can help solve data sparsely and achieve great performance. And the proper dividing ratio lambda achieves the best balance between the history construction and the treatment effect estimation, and thus achieves the best performance. So to conclude, we use uplift modeling to formulate the user interest exploration, and we propose two effective estimation strategies to help solve the interest mining problem, and the effectiveness is validated by extensive experiments on debiased tests of real-world data sets. And in the future, we plan to extend our approaches to session-based models and reinforcement learning. And furthermore, we will explore different actions and treatments to apply our methods to various scenarios. And thanks for your attention. For more information, please refer to the paper and feel free to contact me with my email. Thanks.